Okay, so this is the last half of this virtual lecture, and hope you guys are enjoying it. And I'll give some feedbacks after I come back. So the last topic I want to mention is about torsion. So as you guys know, torsion is another type of deformation. Like the easiest example is steering wheels. Everybody drives cars, right? So for example, a steering wheel maybe somehow looks like this, for example, a traditional one, right? Then when you use your hand to turn the steering wheel, you are applying torque. In other words, there's torsion deformation happening, okay? And or there's another way is like, use a wrench. If you have a hexagonal shape of a nut, right? Let's see whether I can draw a three-dimensional one, something like that, right? So anyway, when you use a wrench to turn it, you are applying torque as well. So in other words, this screw or this bolt is going through some torsion deformation or movement, all right? So in other words, torsion is very similar to a bending, but it causes rotation, okay? So therefore, it's another common deformation you'll see in a lot of material structures. So let's quantify these things. Now, like I mentioned, torsion is caused by torque, T-O-R-Q-U-E. Okay. All right, so if you turn the steering wheel using hand, you're applying torque to the steering wheel, okay? So torque, in other words, it's defined as a moment that tends to twist a member. Okay, so it has to twist a member about its longitudinal axis. Okay, so it's causing a member to twist about its longitudinal axis. All right, so of course, when you have a torque, you'll have some effect, just like when you apply a force to a member, it causes deformation, right? Remember, we have strain equal to stress over Young's modulus, and stress is nothing but force over cross-section area, right? Force causes elongation. Remember, I had an example of stretching a rubber band, right? Okay, so same thing there. And also, there's another important information is chances are when you apply torque, you also cause some deformation. But what kind of deformation or what kind of movement it causes? Let's summarize here. So there's also effects of applying a torque. Okay, so first of all, you will have member twists. Okay, just like the steering wheel, it twists, right? Okay, and also we have effect called the cycle remains a cycle. So in other words, there's no plastic deformation, or there's a no elastic deformation. So in other words, there's no deformation whatsoever. So no elastic or plastic deformation. Okay, it just caused a twist. And lastly, a longitudinal straight line becomes a helix. Okay, so just imagine I cannot show you a video right here, but I can show you a video after I come back. You guys know this thing, drill bit, right? Everybody uses drill bit, right, to drill a hole. So the way they fabricate this drill is by heating up this stainless steel cylinder to a very high temperature, and then you apply a lot of mechanical torque on it, and then that twists it, and then once it cools down, it stays the same shape. So therefore, that's your drill bit. All right. So in other words, a longitudinal straight line becomes a helix. In other words, just like a drill bit. Okay. All right. So and then there are lots of deformation. There are lots of assumptions here, and I'll try to summarize some of the assumptions in talk, and then I'll probably give you 3 examples, and then we should be able to know how we can quantify the torque and the torsion. Okay. All right. So first assumption. The first one is every cross section remains plane. Okay, so in other words, imagine the this boat right here. Okay, so when we twisted that, every single cross section remains plane. So there's no out of plane deformation. In other words, you're not making it longer or shorter. Okay, all right, and also important assumption. These radial lines on the cross section remain straight and rotate through the same angle. All right, it's hard to understand, but let me explain to you. So I think it should be clear. Okay, so radial lines on the cross section remain straight and rotate through the same angle during the deformation. Okay, so imagine we have a cylinder, and then I apply torque. Remember the steering wheel. Okay, now if I artificially have these 2 lines across the steering wheel. Okay, so when I turn it, this line becomes, these 2 black becomes these 2 red because you have deformation. Imagine this line turns here, and then this line turns here, right? Okay, now tells you every single point on this black line, eventually it's going to be the same on every single point here. So if before the deformation these 3 points are on the same line, same radius, after deformation they're also on the same radius or same line. Okay, so there's no non-uniform deformation on the cross section, in other words. Okay, all right, so enough definition said, and then next let's see some equations. Okay, so the important equation here is, first of all, these torsional stress, they are linearly distributed, or linear distribution of stress. In other words, so think about this. When you have a cylinder, so let's say a cylinder, certain length, right? The body is fixed. And then on the surface, apply certain torque. I want to turn it. Imagine this is a screw, but it's like it's bonded to the ground or bound to the surface of the wall. Okay, and I use a wrench trying to turn it. Okay, now if I want to turn it, there's a special point which is right in the rotational center. It has very small amount of stress, which I'll show you later. Right, so the stress being applied, tau, is nothing but T times C divided by J. Okay, so let's look at the surface. T is of course the torque you apply. And again, according to definition, torque is a moment, right? So what's the unit of moment? That's right, Newton times meter, right? How many newtons times how many meter? Okay. Now, J is also a polar moment of inertia. So this polar moment of inertia is determined by material property, just like area moment of inertia. You guys learned that in statics, and I'll show you how to calculate this polar moment of inertia later on. Okay. All right. This C is distance to rotation center. All right. For example, rotational center, like I mentioned, has no stress whatsoever, right? And tau is shear stress, by the way. Okay, just like what we did before. Now, total radius, I know it's r, right? If I find an arbitrary point right here on the surface, let's say this is my point A. Now, the distance between the rotational center O to A is OA, right? Let's say this distance is C. So OA equals to C, an arbitrary point, and then the total length is C. So at a point A, the amount of shear stress is equal to Tc divided by J. Make sense? T is the torque applied, and C is distance from the rotational center. And then J is polar moment inertia, which I told you the detail, how to calculate that. It's a material property once it's fixed, okay? Once the dimension is fixed. Already. So in other words, if I only look at the cross-section area, okay? Now I know this tau equal to T divided by J times C. Let's write this way, right? I write this way on purpose. Now, T is a torque applied. J is polar moment of inertia. It's a material geometry property. So in other words, this is a constant. Okay? The torque applied is always there, right? J is material property. Now, the only variable is C. So C is distance to the rotational center. So tell me, when I look at the shear stress right in the rotational center, what is tau should equal to? In other words, when C equal to 0, tau equal to what? Of course 0, right? That tells you in the rotational center, there's no shear stress. Okay, make sense? All right. Now, next thing is tau. It's linearly increasing with the distance. So if I draw that, let me use a different color. Let me use red. Okay, so it's a linear to the center. So you can imagine the stress, chances are it looks like this. Right? Everything's linear. So at this point, stress is high. Slowly decrease, all the way to 0. Right? So that tells you, here I have a question for you. What is the maximum shear stress can be developed? Okay, let me write here. That's of course when C equal to max, right? The distance to the rotational center has to be max. So what is C max? C max, I say, equals to the radius, right? Because the highest distance to the rotational center is radius, right on the surface. So for example, if this point right here, then that is radius, okay? So that tells you tau max equal to Tj times R, okay? R being radius, make sense? So that tells you the maximum shear stress always happens on the surface of the cylinder when it's further away, when it's furthest away from the rotational center, okay? All right, so remember these two equations. They are very important. We will be using them for the examples, okay? Alrighty. Okay, all right. So next thing is this J term. J. Okay, so this J term is, like we said, it's called polar moment of inertia. Okay, now I just give you two simple ones. One, cylinder. By the way, in the future, if I give you any arbitrary shape, rectangular stuff like that, I will give you this J. Right? You do not have to remember how to calculate this J or stuff like that. It's a material constant. You should be able to use a either you can find that in the back of the book. If not, ask me. Okay, I'll give it to you. So J is all the way. In other words, if you want, try to write that in your cheat sheet. That'll do it too. Okay, J equal to pi over 2 c times the force. All right. So what's c? C is the radius of the circle. Okay. Now sometimes we like to use r, but it's the same thing. So let's just write or pi over 2 times r the force. All right, but in this case we don't want to confuse you guys, because r sometimes it looks like a gamma, and it's also rotational angle, so we like to use c for this case. Okay, already. And so this is J equals to, we have a solid cylinder. solid cylinder. Okay. All right. Now sometimes you also have hollow cylinder. In other words, only the outside and to a certain degree there's a materials. There's no material in the center. Now, why do we use hollow? Take a guess. Remember this equation, right? Material property, shear stress is proportional to the distance. So what is the shear stress inside here? Chances are, if it's at the rotational center, it's 0, right? And then all the shear stress here is very small, and it becomes bigger and bigger with the increase of the radius, right? So that tells you if your material is undergoing torque, the material in the middle, what? They have no or very small amount of shear stress, right? So therefore, that material does not carry much load. So we can just use the hollow tube for the application we want. Make sense? Because the material in the center does not carry that much of load at all because of this equation. Okay? Already. So if you have a hollow, then I'll show you how do we calculate that. So first of all, you have two radius. The radius we call that CI, internal, and then CO. Okay, internal radius, outside radius. So in that case, J equals to pi over 2 CO, the force, minus CI, the force. Okay, all right, write these two equations down in your cheat sheet in the future. You will be needing them. Okay, alrighty. So that is it. Now, okay, so we learned this new concept, relatively speaking. It's fairly easy to understand, right? We know torque is a moment, and then that causes rotational deformation, right? I shouldn't say deformation; it's called rotational movement, and then we can use that to solve for some of the things, okay? Just like how much force we needed to turn the steering wheel, for example, right? Okay, so before I give you the three simple examples, let me give you some guidelines, okay, in terms of how we can use this knowledge to solve for it. So I'll summarize this thing into something called procedure for analysis. Okay, so the first thing, step 1, we need to determine internal loading. Okay, in other words, the most important thing is torque or torsion, they have built-in shear stress. Okay, all right. So the way we do determine internal loading is we need to section the shaft perpendicular to its axis at the point where the shear stress is to be determined. Okay, of course, we need to section the shaft perpendicular to its axis. Basically, we need to find a cross-section area, right? And then we need to do the stress analysis. In other words, free body diagram. Okay, we need to do that. Now, second, it's called section property. Okay, so we need to find J of the cross-section area. If it's a solid, just use pi over 2, see the force, right? If it's a hollow, then just pi over 2, CO minus CI, both force power, okay? Okay, so we need to compute or calculate. Lastly, calculate the shear stress. In other words, using this equation, T times, let's say, certain C, okay, times J. Now, in the textbook, occasionally they also use T times rho divided by J, right? So make sure you know rho is also distance to rotational center. Maybe, for example, right here, you have rotational center, and the distance from this arbitrary point A to O, we can also call that rho. Okay, doesn't have to be called C. Okay, just to let you know. All right, so easy, 3-step: free body diagram, computer the J, and then find out the shear stress. Okay, very simple. So next, let's look at a simple example so we can get things going. Okay, first of all, we have is a solid shaft is fixed to the support at C and subjected to the torsional stress at A and B, 2 points. Okay, so calculate the shear stress on these points. Okay, so basically this is solid shaft fixed to the support at C, and then there's a torque being applied, and then it's asking for the shear stress at 2 points. Okay, so let me show you that. So this is a straightforward problem. Okay, a cylinder, right? And C, this is my end point, so it's fixed to the wall. Okay, fixed. Then you have a 2 torque being applied. One is a going towards clockwise direction, 10 kilonewton times meter, and there's also another one applied way further down here. It's a 4 kilonewton times meter. Okay, so 2 torque applied. All right, and then the radius information is given us. So the radius, let's just use C, equals to 75 millimeters. Okay, so C equal to 75 millimeters radius. Okay, there you go. All right, so there's 2 points on the line, right? The first point is called point A, which is further down here. And then let me try to use blue color to draw the rotational center line right here, axis. Okay, all right, so this point A, it's about 50 millimeters away from the rotational center. Okay, so point A, the distance from here to here is 50 millimeters. 50 millimeters away from rotational center. Okay, that's the distance from A all the way to the rotational center. Also, there's another one, which is B. Now B is a special point because it's right on the outside of the radius. So this distance over here, B, is 75, which is equal to the radius. Okay, all right. So the way we do it is, of course, we need to do free body diagram, right? Now, here's something important. Okay, look at these 2 points, A, and also there's a B. Okay, so these 2 points, they are on different locations along the rotational axis, right? Okay, so we need to do free body diagram on these 2 things, right? When you do free body diagrams on these 2 things, things will be a little different. Okay, so let's just say, let's look at free body diagram, just one line. Now this is fixed and C, okay? Now you have a torque going that way of 10 kilonewton times meter, and then you also have another torque coming here. That's 4 kilonewton times meter. Now, let me also explain to you how you can determine direction of the torsion. Okay, I think it's hard to explain to you right now because you cannot see me. But basically use your right hand. Okay, now your four fingers is this rotational center of the torque, and your thumb will be the direction of the torque. Now, for this 10 kilonewton times meter, four fingers is rotational center, use your right hand, okay? And your thumb is direction of the torque. So in other words, this torque over here going to that way. Let me use a different color. Okay, so over here. So we use double arrow for moment, okay? Because torque is one type of moment, okay? Now single arrow is for force, right? So that's the direction of the torque. Now you would imagine for the 4 kilonewton time meter, still use your right hand, okay? Now these four fingers is the direction of the rotation, and your thumb is the direction of the torque. So it goes this way, okay? Now, if you cannot understand that, or if some of you really have a hard time, don't worry about it. After I come back, I'll explain to you in person, okay? All right, so point A, as you can see, it's further down here. Maybe let's say orange color, somewhere over here. Somewhere over here, right? Well, the blue is in between, so therefore, point B is in between, somewhere over here. All right, so the torque applied on point A and torque applied on point B, they are different, right? Because one of the torque, 10 kilonewton, goes to the left, and then the other torque, 4 kilonewton, goes to the right. In other words, they cause different direction of rotation, right? Okay, so we need to consider these two torque differently. So at point A, the torque summation T equals to, let's just say 10 minus 4, because let's say the 10 kilonewton is positive, and then of course the other 4 is negative because they're going different directions, right? One is clockwise, the other counterclockwise, or use the right hand rule I mentioned. One of them goes to the left, the other one goes to the right, right? So summation T at point A is equal to 6 kilonewton time meter, okay? And then at B, summation TB, I say it's right equal to 4 kilonewton time meter, right? Because imagine if you section this here, right? Section at B, you see there's only one torque going that way, which is 4 kilonewton times meter. Of course, at the point B, this torque here is 4 kilonewton, right? And at A, the same thing. If you want, feel free to do a free body diagram, right? 10 minus 4. You'll see that. I only look at the absolute value, okay, by the way, because that's what we need to calculate the maximum or the shear stress, okay? Alrighty, so this is our step 1, free body diagram, find the stress, right? The next step is what? Remember, step 2, calculate the J, right? J is pi over 2 times the diameter, which is 0.07575 millimeters, times the force, okay? Use your calculator. I cannot calculate this by hand. Times 10 to the minus 6 meter the force. Okay, so that's my step 2. What's step 3? Use the equation, right? So tau B equal to TB times the distance, which let's just say B is a C, right? Because it's a radius. So we can use C or R for radius, divided by J. Okay, so therefore plug it in. TB is 4 kilonewton, don't forget 10 to the 3. And distance to the rotational center at B is the radius, which is 0.75. And the J is 49.7 times 10 to the minus 6. So therefore, answer can be calculated 6.04 megapascal. Okay, now the next tau A, same thing, equal to TA divided by C divided by J. Oh, sorry, not C anymore. The distance to the C, let's distance to the rotational center, let's just say rho A. This TA we calculated 6 kilonewton times meter, and distance to the rotational center, let's say right here, 50 millimeter, right? It's given. So 50 times 10 to the minus 3. Divide by 49.7, same J, right? Because the diameter is the same across the whole length, times 10 to the minus 6. then your answer is about equal to also around 6.04 megapascal. Answer. Right? Okay, so although rho A is smaller, but here A is bigger. Okay, so that's why they end up to be the same shear stress. But this doesn't happen all the time. Okay, only the special case is because the torque at B is smaller than that torque of A. Okay, alrighty. So this is how you calculate this out. Now, of course, I cannot have a question and answer session, so therefore, if you have any questions, just hold on that, all right? And then after I come back on Tuesday, I can explain that to you in person and in details, okay? Alrighty, so let's see, maybe let's do one more example, shall we? Okay, all right. Okay, this one will be relatively speaking simple. So example, come on. Okay, so if the 40 millimeter long, 40 millimeter diameter rod is subjected to a uniform distributed torque of TO equals to 1.5 kilonewton times meter divided by meter. So in other words, it's a torque just like a distributed load. So this is distributed torque. So therefore you have torque over certain lengths, right? Makes sense? Just sometimes I like to call it torque density, just like distributed force. That's distributed force density. Okay. So this is torque over per unit meter. Okay. Now determine the shear stress developed at point C. Okay. Alrighty, so again, there's a rod, diameter equals to 40 millimeters. So in some case we use C, right, by the way. Okay, so there's a special point C, which is right in the middle, and on the outside of this radius, okay? Now, distance from here to here, here to here is 300 millimeters a piece, okay? So each one is 300. Then this point C is all the way on the outside of the radius, okay? And then this is my point A, this is my point B, and again point A is fixed. Now this will have a uniformly distributed torque, let's say just like that. Okay, so therefore it causes rotation across the whole length. Okay, already. So the first thing first is we need to calculate what is going on in this internal force, right? So the way we do it is we have a free body diagram. So the total torque being applied here, we know T is equal to, of course, 1.5 times 10 to the 3 kilonewton times meter times the distance, right? So right at a C, let's just use a section tool right here. So right at a C, we know the length is 300. So this L from all the way from A to B, we know it is equal to 1. Let's say this DC 5 times 10 to the 3 times 0.3 because it's 0.3 meters. It is 1.5 kilonewton meter per meter, right? So everything is in meters, so transfer that to meter. So 300 millimeter is 0.3. Okay, so we can calculate the torque at C. Then the rest should be easy. And then step 2, J pi over 2 times C the force, right? Pi over 2 times 0.02, because that's my diameter equal to 40. So therefore, C, or radius, is 20. Don't forget that, okay? So transfer everything to meter. Then you'll have answer roughly equal to 80 times 10 to the minus 9 pi meter the fourth. Okay? Alright, so next is easy. Using our equation, tau c equal to tc times the distance, let's say rho c, which is equal to exactly the radius c, okay? Because it's on the outside. So 1.5 times 10 to the 3 times 0.3, that's my torque. And then the radius is 0.02, right? 20 millimeters. And then the other one is 80 times 10 to the minus 9 times pi. That's my polar moment of inertia. Use your calculator to calculate your answer, 35.8 megapascal. That is the answer. Easy, right? So 3-step. Internal force analysis, find the J, and then find the tau. Okay? Alright, I am going to stop here, and then if